Okay, so at this point, you can type your name in for attendance. Write that. So welcome everybody. I hope you all had a good week. I hope you're doing fine and feeling well. I wanted, before we start talking about any of the math, I wanted to let you know that I do have the website back up and running in case you want to find any of the old lecture notes. So I'm going to type it here. I'm going to type it on the chat also. So it's a new website. So the new website is this, blogs.baruch. Let me see, actually, do I have it just here? No, HTTP blogs.baruch.cuny.edu/aobus. And then what do I need?
Yeah, Jamal.
One second. Hi. Sorry, I'm trying to get the full web address because I never completely remember it. So Liberian mathematics teacher training program. So let's try this /Liberian mathematics teacher training program. HTML. Yeah. Okay. So this is the new website, by the way, if anybody wants to click on it. It doesn't have that much on it right now, but it does have a link to all of the lecture notes from this semester. And it also has a link to my YouTube page where all of the recordings of the talks are. So I'm also going to send this link to the chat. So if you ever need to find any of the old lecture notes, they're all here. My old website is not working because my university had a cyber attack earlier on and it brought down the faculty server. So now I have a new one and this is where you can find everything. Okay. So I'll continue to post everything on this website. Right now it's just the syllabus, and actually the syllabus may not work. Yeah, the syllabus is actually not linked. I need to link the syllabus, but it does have good links to all of the lecture notes and to my YouTube channel. Okay, great. Okay, so we're gonna finish up our geometry unit today. We'll probably spend a little bit of time going over the homework because there were a couple of tricky problems on the homework. And then I'm going to talk a little bit, we've been talking about Euclidean geometry this entire time, geometry in the plane. So I'm going to spend a little bit of time today talking about what's called non-Euclidean geometry. And non-Euclidean geometry is doing geometry, but you're not necessarily in the plane. So for instance, doing geometry on the surface of the Earth where things are curved instead of just being on the plane, or there's also something called hyperbolic geometry. So we'll mention both of those things, and that'll kind of conclude this geometry unit, and then we'll decide what we want to do for the rest of the semester. I'll send out a survey that will where you can give your input as to what you'd prefer to do. Okay, but to start with, let's just start by going over the homework. The exercise 1 is fairly straightforward. 2 and 3 are maybe the more interesting ones, but let's go through exercise 1 first. So the question is to find the center and radius of the circle given by this equation: x squared plus y squared plus 8x minus y equals 20. So I claim that this is a circle, even though it doesn't look like the equation for a circle that we had before. Maybe I should just recall over here, for a circle, we have x minus a squared plus y minus b squared equals r squared. And this is for a circle whose center is at AB and whose radius is r. Okay, this is the equation for a circle like that. So what we have to do for this problem is to figure out a way to get this equation in the form of this so that we can read off what the center and the radius are. Okay, so does anybody want to give a try for how we modify this equation to get it into the standard circle form?
Yes.
Yeah, Ed?
Yeah, okay. So the first thing we have to look at the like terms. That is by saying x squared plus 8x plus y squared minus y equal 20.
Great.
Then the next one we do find half of the middle term of each.
Right. So dividing this by 2 gives us 4, and dividing this by 2 is giving us 1/2.
Yes.
Great.
So we have x plus 4 all squared.
Right. So this is going to be, so x plus 4 squared.
Plus y minus 1 over 2 all squared.
Right. Plus y minus 1/2 squared. But now we have to add something in, right? Because this x plus 4 squared is x squared plus 8x. So what do we have to add in over here or subtract?
Plus. So we have to add plus.
Sorry, there's too much background. Sorry, I just needed to mute everybody. But Ed, you can unmute yourself and continue.
Yes, plus.
Yeah, plus. So plus what?
Equal to 20 first.
Yep.
20 plus 16.
Okay.
We have to square in half.
Right. So why not I actually write it I'm just going to throw in one intermediate step. I'll write a minus 16 over here, just because this x squared plus 8x is x plus 4 squared minus 16, right? Because it's x squared plus 8x plus 16 minus 16. So that's fine. In the end, it's going to be the same. And so over here, I write a minus. Ed?
Yeah, minus 1 over 4.
Minus 1 over 4, exactly. Right. So now we can do what you wanted to do, which is move this to the other side. So x plus 4 squared plus y minus 1/2 squared is equal to 20 plus 16 plus 1/4. Okay. And so continue.
So then we add 20 plus 16. We have to find a radius. 20 plus 16, that will give 36.
Yeah.
Then we have 1/4. So that's a fraction. So we have 36, 1/4.
Yep. Right. So this 36 and 1/4, which if we want to put it all together is 145 over 4.
Yes.
Okay. So what do we get? So the center, yeah.
The center is A comma B, and A is 4, B is minus 1 over 2.
So we just have to be a little careful, right? Because the standard form is x minus A and y minus B. So if we have x plus 4, we actually have to rewrite it as what?
Minus. Yeah, so we have minus 4.
Right. X minus minus 4, right? Yeah. And then plus
y
1 over 2. Right?
Okay, yeah. Minus 4, 1 over 2.
Minus 4 and 1 over 2, right? Because we have the x plus 4. So that means you have to rewrite this as x minus minus 4 to be in this form. Yeah. And so the minus 4 is going to be the center. Here, you don't have to do anything. You already have y minus 1/2, so you can just use 1/2 over here. Great. And then what is the radius?
The radius will be, we have 145 is now a perfect square.
No, it's not a perfect.
We have the 4 that would be a perfect square.
Yes. Right.
So we have to take the root of them. 145 over 4.
Right. And so the root of 145, we can't do anything about. That just stays the way it is. But the square root of 4, if we want to, we can rewrite that as 2.
Yes.
Okay, great. So that is correct. So that's the full answer, right? So thanks, Rufus, for the comment there. And yeah, so this is exactly right. So the center of the circle is minus 4, 1/2. And the radius is the square root of 145 over 2. And if we want to, we can write that out as a decimal. And that's going to be about 6.02. Okay, so which makes sense, right? Because square root of 145 is a little bit bigger than the square root of 144, which is 12. So you add 1 and it's going to make things slightly bigger. Okay. Good. All right. Any questions? Yes, Abraham.
What you have the bracket on the 4x+4 all square. What you have the bracket that are in red. I think it should be x minus 4 bracket open plus 4. X minus bracket open plus 4.
Oh,
So
okay.
the 4 in the bracket there is positive.
You mean over here?
Yeah.
Yeah. Well, so I mean, x plus 4, right? I mean, this is x plus 4, right? So sorry, let me try to talk a little bit closer to the microphone if you're not getting me. So maybe this is better, right? So we have x plus 4 is the same thing as x minus 4, right? We're not actually doing anything to this. I'm just rewriting the expression with something equivalent. Okay. So it's just x plus 4 is the same thing as x minus 4. I'm not actually subtracting or adding anything here. Okay, so I'm just rewriting this just so that it looks like something in the form x minus a, because we need to know what a is in order to get the center. So if I have x plus 4, I need to rewrite that somehow as x minus something. And so that something has got to be a over here.
All right.
Okay. All right. Any other questions? Okay. Okay. Okay, Armstrong, hopefully you're getting me a little clearer now. Okay, good. So let's do the next exercises. So number 2 is maybe the most interesting exercise. So we have a circle inscribed in an equilateral triangle. So I have a triangle here, and then I'm going to have this circle that's inscribed here, which I'm generally pretty bad at drawing, but we'll do that. So we have a circle, it's got a center here, and what I told you you can use, this is a result from geometry, is that the distance, the radius of this circle, the distance from this side up to the circle is 1/3 of the total altitude of the triangle, right? And so what we want to do is find the ratio of the circle's area to that of the triangle. And I haven't told you how big the triangle is, right? But that shouldn't matter, because whatever if the triangle has side length 1 or side length 2 or side length 3, none of that should matter, because if I scale up the triangle, the circle is going to get scaled up by the same factor. So in fact, the ratio, which is what you're being asked to find, the ratio of the circle area to the triangle area is not going to change. Okay. So I know that at least I saw at least one correct solution here, and some other solutions with some correct ideas, even if there was a little mistake in it somewhere. So does anybody want to start off? How do we even start this problem? What kinds of labels can we put on this diagram to make it work? Okay, it's very low on your screen, Armstrong. Maybe you need to go in and go out, because I think it should be okay. Yes, Gabriel?
I think we can say the triangle is an equilateral triangle.
Yeah.
We can draw a line from the center. Also, we can get a radius from the center to the hitting one point to the triangle.
Okay, so like draw this line?
Yes.
Okay.
And try another one.
Okay.
So the line through, send the triangle, since each angle in the triangle contains 60 degrees.
Right.
The line through will divide the angles into 2. So
yeah,
that will take 30.
Good. Okay, so 30 degrees. Let me rewrite that somewhere. Let me just say. Great. So everything here is 30 degrees. Mm-hmm.
So, but can we label the triangle?
Mm-hmm.
Can we label it as A, B, C, D?
Okay,
E?
so the triangle, put A, B, and C at the corners.
Yeah.
Okay.
And D, we can call it
D is here.
the middle, in the middle there.
Okay. Oh, D up here. Okay. Sure.
There, in the middle there is the center. I'll take
Okay,
the
we'll
middle to be the center.
call that
Or we
in the
use
middle, so
O.
we'll call that O in the center?
Yeah.
Okay.
Yeah.
And then D over here?
Yeah.
Okay. Okay, so
So
we're gonna,
for me,
yeah. And do you want to
okay,
give the side of the triangle a length? You want to give the length a name?
yeah, maybe we can call it, X.
X. Okay, great. So we'll call the side of a triangle is going to be X. So we're
Yeah,
going to
every
need
side there
two
will be
things.
X.
Yeah, so all of them are X. So I'll write this here, X, X. So we're going to need to do two different calculations, right? The area of the triangle and the area of the circle.
Okay.
Okay. Mm-hmm.
Okay.
So which do you want to do first? Which area should we do first? The area of the triangle or the area of the circle?
Let's do the area of the triangle.
Okay, so let's do the triangle first.
Yeah, do the triangle first.
Okay. So for the triangle, I mean, we have a formula for this, remember, because we did do a formula for the area of any regular polygon, including an equilateral triangle. But we can also figure it out ourselves if we want to use a little bit of trigonometry, right? So if we want to use some trigonometry, we can figure this out, right? We have X over here, and this is the altitude, right? So if we want to do altitude, well, we know that the altitude divided by the hypotenuse is going to be equal to, that's the sine of 60 degrees, right? So we can say altitude divided by X is equal to sine of 60 degrees, which is equal to square root of 3/2. And this implies that the altitude, which I'm just going to call H, we'll call it H. So this implies that, that H equals square root of 3/2 times X. Right. Okay, so if the height is square root of 3/2 times X, then what's the area of the triangle? Area of the triangle, right, is 1/2 times X, which is the base, and times the height. And if you substitute in H equals square root of 3/2 times X, then this becomes square root of 3/4 times X squared. Right, so this is the area of the triangle. Okay. So is that okay? Any questions on how we calculate this?
Well, this is very short, you see.
Yeah. So
yeah,
there are
we
ways of doing it.
we went to it. It was still derived as a result, but we make our own logo.
Oh, okay, okay.
Yeah, for the area of the triangle.
Yep. So the area of the triangle. And, we have, if you look in earlier notes, we have this formula. So you can just use the formula if you want, but it's good to know how to rederive it by calculating the height or the altitude of the triangle. Okay. Okay, so now what about the circle? We need to know what's the radius of the circle. So how do we figure out the radius of the circle? And you can use the hint, or in fact, with your angles, you don't even need to use the hint. You can figure it out yourself. So what should the radius of this circle be? Sorry, Clinton, I'm not getting you. I'm not getting you, Clinton.
Yeah. Yeah, hello?
Hello, yeah, Gabriel, yeah.
Yeah,
Yeah, Gabriel?
yes, we can use trigonometry.
Yes, so actually, yeah, let's have Gabriel do this. I'm getting him a little clearer. Yes, so we can use trigonometry again, right? So the radius is this r over here, right?
Yeah, so B, I should get results?
Yeah. How do you do the radius?
So
what's
OB,
the trigonometry equation? Yeah.
OB opposite over adjacent. Where we can label AT to be the adjacent side.
Right, exactly. So we have
so B tangent 30 degree.
Right. And so what
degree.
Tangent of 30 degrees, right? Because here we have this 30-degree angle, R is the opposite and AD is the adjacent, and so the ratio is 10 of 30 degrees. Good?
Yeah, so AD will be S over 2.
Great, exactly. And tangent of 30 degrees is what?
Tangent of 30 degrees will be root 3 over 3.
Exactly. Good. So we can solve for this here, and we get that R is going to be equal to X times square root of 3 divided by 6. What this comes out to be. Is you multiply this by X over 2. So you multiply square root of 3 over 3 by X over 2, and that becomes X times square root of 3 over 6. Maybe let me just write out the extra step. So R is equal to square root of 3 over 3 times X over 2, which is equal to square root of 3 over 6 times X. Okay. Good. Okay, so that means the area we know is pi r squared, and so that's pi times square root 3 over 6x squared, right? Which is equal to okay. So that's going to be pi times 3 over 36 x squared, which is pi over 12 times x squared. Okay, so this is the area of the triangle, and this is the area of the circle. Right, so the triangle is square root of 3 over 4 x squared, and the circle is pi over 12 x squared. So we need a little bit more space here. Let me just clear a little space over here. So now we need the ratio. So that's area of circle divided by area of triangle. This is going to be equal to pi over 12 x squared divided by square root of 3 over 4 x squared. And well, the x squareds cancel out. And we end up getting that this is equal to pi over 12 times 4 over square root of 3. And we can cancel out a 4, and this becomes a 3. And so we get that this is equal to pi over 3 times square root of 3. Okay. So pi over 3 times square root of 3, and let me just calculate what that is as a decimal. So pi divided by 3 square root of 3. So it's about 0.604. About 0.605, 6046, let's say. Okay. Okay, so this is a bit of a tricky problem. It's a little bit of a multi-step problem here, right? You have to calculate the area of the triangle and the area of the circle, and then you have to find the ratio. And to do the area of the triangle, either you need to remember what the formula is for an equilateral triangle, or you have to use trigonometry to figure out what the altitude of the triangle is. So square root of 3 over 2x. And then for the area of the circle, you need to know the radius. And the radius, you can either just use the hint that it's 1/3 of the altitude. So if the altitude is square root of 3 over 2x, then the radius of the circle is square root of 3 over 6x. Or if you want to, you can use trigonometry to figure it out. And you get that r over x over 2 is tangent of 30 degrees. And when you do the algebra and solve it out, you end up getting that the radius is square root of 3 over x. Once you have the radius, you can use the formula for an area of a circle in order to get that the area of the circle is pi over 12x squared. And then you can take this ratio. And so we get with this ratio is that the circle takes up about 60% of the triangle, right? The ratio is 0.6046. So it's a little more than 60% of the triangle is area taken up by the circle. Okay. Questions? Is that okay?
Thank you.
Okay, you're welcome. Thank you for the answers. So let's do number 3 now, which is a little bit easier. So 3, we just have a square, right? It's the same question, but we have a circle inscribed in a square. So let's try to draw our circle here inside a square. Again, I don't necessarily do it so well. And we can use the same notation that x will be the side length of every square. So in this case, the area of the square is very easy. The area of the square, of course, is just going to be x squared, right? So now what we need is the area of the circle, which shouldn't be that hard either, because we just have to figure out what the radius of the circle is. So what's the radius of the circle in this case?
Is x over 2.
Exactly, right? It's just the radius is just halfway up the square, right? So the radius is x over 2. So the area is pi r squared, which is pi times x over 2 squared, which becomes pi x squared over 4. Right. Okay. So now we just do the ratio. The ratio of the circle to the square, we have pi x squared over 4 divided by x squared. And this comes out to be much easier. We end up just getting pi over 4. And this is roughly, it's about like 0.785 or something like that. So pi over 4, yeah, it's about 0.785. Okay, so this is the ratio here, is 0.785. And if you notice, compared to the triangle, right, 0.785 is bigger, right? So when you have a square, the circle takes up 78.5% of the square. Whereas when you have a triangle, the circle only takes up about 60% of the triangle, right? So the circle fills up more of the square than it fills up with the triangle. So the question is, does this suggest a pattern? So let's say we did a pentagon or a hexagon or an octagon or something like that. What would you expect happens to this ratio? So the area of the inscribed circle versus the area of the entire polygon. Clinton?
Yeah. Mm-hmm. So in my solution, I said that if we look at the first ratio, because remember we are talking about we're talking about regular polygons. The triangle, equilateral triangle is a regular triangle, and the square is also a regular quadrilateral.
Yeah.
So I assume that the remaining polygons, the far-sided polygon and stuff, will be regular polygons. And then,
sure, yes, regular polygons.
My suggestion was that the ratio between the ratio between the area of a circle inscribed in any regular polygon will be increasing based on the value of the number of sides the polygon has. That was what I suggested.
Yeah, and that's
so
exactly
the ratio
right.
will always increase, as I said.
And that's exactly right. So the ratio will always be increasing. And in fact, it's going to go up to a limit of 1, right? So if the polygon has lots and lots of sides, the more sides you add, the closer and closer this ratio is going to get to 1, right? 1 would be if the circle fills up the entire polygon. We know that it never does that, but look what we have. We have like 60%, then we have 78.5%. A pentagon would be a little hard to calculate this, but for a hexagon, it wouldn't be that hard. So you could calculate this for a hexagon if you want to. Actually, I don't know off the top of my head what the answer is, but imagine, look what happens when you have a lot of sides, right? So let's say I have an octagon. Well, the more sides my regular polygon has, the more it starts to look like a circle, right? So if I'm inscribing a circle in a regular octagon, then this circle is really taking up, the circle is a large part of the area. And then what we have is the more sides in a regular polygon, the larger proportion of the area the circle takes up. Okay, because if you have really a lot of sides, it starts to get hard to even notice that it's not a circle. If a computer draws you a regular polygon with 100 sides, it's just going to look like a circle, right? It's not going to look any different. In fact, maybe I can, let me just see if there's something like this on the internet. Regular 100 gon. If I want to look at a picture of a regular 100 gon, it basically just looks like a circle. So sorry, 1 second. Sorry, 1 second. I'll be right there. Oh, can you get it? Okay, thanks. Sorry. Yeah, so let me actually just show you this. So if I show you sharing screen. So if we look right here, if you see, this is a regular 100. Don't want my audio to come back on. Sorry. So this picture right here is a regular 100 gon, right? And if you look at it, it basically just looks like a circle, right? It has so many sides that to your eye, you can't even see the difference between this and a circle, right? So if I draw the inscribed circle here, then clearly it's going to take up almost all the area. It's not going to be exactly the same, but I would think this circle will take up at least 99% of the area if I inscribe a circle inside this regular 100 gon. And so the more and more sides, the closer it looks like a circle, and that means that the inscribed circle is going to take up almost all of the area. So in the limit, if you know some calculus, in the limit as n goes to infinity with the number of sides, this ratio goes to 1. But it's going to keep getting bigger and bigger the more sides you add. Okay. Any questions?
Yeah.
Yep.
Andrew,
yeah.
Yeah. So this is very important. It is very important because when I wanted to do my suggestion, I was not thinking about the limit actually approaching 1, but I want to know whether there is a particular generalization we can do in terms of a formula of n, in which when we find the limit of that formula, we get 1.
Yes, you can. I don't really have time to do it right now, but yes. Let me tell you, the hint is, if you go back to the notes when we talked about the area of a regular polygon, what we did was we in fact gave a formula for the area of a regular polygon in terms of the radius of this circle. And so we gave a formula. It uses trigonometry for the area of a regular polygon in terms of the radius of the circle. So you can use that formula for the area of the regular polygon, and then you can also just the circle is just pi r squared, and then you can take that ratio, and that will be a formula whose limit will go to 1. But it's not, that limit's not so easy to prove. It's the geometry is kind of what gives it to you.
Oh, okay. Right.
Yeah, I can tell you more afterward. I think it's going to take a little too long to do it all right now.
All right, no problem.
Okay, great. Other questions? Okay, let me stop this share and then reshare my screen. Screen. Okay, good. All right. So okay, so we took a lot of time with the homework, but I think this was important because these problems were fairly difficult. Okay, so the rest of today is not going to be so much calculation. It's going to be a little bit of philosophy of geometry. So, it won't take too long to do. So what I want to talk a little bit about is what's called the parallel postulate in Euclidean geometry. So when we started the geometry unit, I mentioned that Euclid's approach to geometry was to start with what he called postulates, or they're also sometimes called axioms. There's not really a difference between these two words. They mean the same thing. And to derive all of the results from the axioms using proofs. And these axioms are very basic statements that we just accept that they're true without any proof. So statements like, between any 2 points, there's exactly one straight line connecting the points, things like that. And you start with, some of these results, and then from these basic axioms, you can build up all these proofs. This is what Euclid did in the elements. Things like any 2 right angles are equal, things like this. So one of the most important postulates, though, is sometimes called the parallel postulate or the 5th postulate. And this one is like a little bit less obvious than the other ones. And so what does it say? It states that if you have a line in the plane and a point not on the line, then there's exactly one line passing through the point that's parallel to the line. So this is maybe hard to understand in words. Let me just draw a picture. So this is a point P, and this is a line L over here. And what we're saying is that there's exactly one way to draw a line through P that's parallel to L. Okay, that's the parallel postulate. Okay? And technically, this is not the way Euclid actually stated it. This is something that's called Playfair's postulate. Euclid actually stated it in a different but equivalent way. It's not quite as clear why they're equivalent, but basically, for modern mathematicians, this is what we take as the parallel postulate. So if I have a line and a point, then there's one way to draw a line through that point that's parallel to the first line. Okay? And for really centuries and centuries, mathematicians tried to prove this postulate from the other ones, but nobody ever had a correct proof. People posted lots of proofs trying to prove that there was only one way to draw this line using only the basic axioms of Euclidean geometry. And people published proofs and submitted them, but in the end, there was always something wrong with the proof. Okay? So let me also just say how Euclid actually stated it. What Euclid's actual 5th postulate is this, was that if you had a line and you have two other lines cross it, and they make angles on one side that add up to less than 180 degrees. So if we have like these two angles, alpha and alpha plus beta is less than 180 degrees, and as Euclid would say, two right angles, then Euclid's postulate is saying that if that happens, then these two lines have to meet somewhere. If you extend the lines, they're going to meet somewhere. Okay. They're going to meet over here. Okay, so it's saying if you have these two angles, they add up to less than 180 degrees, then the two lines are going to meet. Okay. And so it turns out that this is equivalent to the parallel postulate, although going through that is actually not that easy and would take a while. So Euclid stated it this way. The modern mathematicians tend to state it in terms of there being only one parallel line through a point, which is, I think, maybe also a little more basic, a little bit easier to understand. Okay. So in any case, you have this postulate that people use. And when you have all of these axioms or postulates together, then the system that you get is what's called Euclidean geometry, which is the standard plane geometry that we're all familiar with. And you can prove everything in plane geometry just from using logic and from using these axioms. Okay? So now, Playfair's postulate, it seems obvious, right? It seems like a weird thing, like we're talking about proving this, but I mean, of course, if I draw a line, right? I mean, of course, if I take a line and I take a point, of course, there's only one way to draw a parallel line, right? And it doesn't seem like this should be that hard. But, you know, around the 19th century, people started to think a little bit deeper about this. So, for instance, let's say that we don't assume that there's exactly one way to draw a line here. So then there were two European mathematicians, a Hungarian mathematician named Bolyai and a Russian mathematician named Lobachevsky. So they discovered what happens if instead of Playfair's postulate, instead of there being exactly one line, we state that actually, what if there's more than one line that passes through a point that's parallel to another line? Okay. And it turns out that this makes some sense, and this is what's called hyperbolic geometry. And around the same time, you could also decide what happens if you say there isn't more than one line through this point that's parallel to this line, but in fact, there are no lines at all that are parallel to this line. And if you do that, you get something called elliptic geometry or spherical geometry. Okay, so this maybe seems a little abstract. So let me actually show some pictures that are going to demonstrate, you know, what's going on. So let's talk about elliptic geometry first, because it's going to be a little bit easier. And so, by the way, both of these geometries are called non-Euclidean geometry, okay, because it's discarding Euclid's postulate. We're not using this parallel postulate that there's exactly one line through a point that's parallel to a given line. Okay, so let's draw some pictures that'll actually make this make some sense. So, well, first of all, let me say a little bit about elliptic geometry, and then we'll do some pictures. So elliptic geometry it's easier because we can think of elliptic geometry as geometry on the surface of the Earth. And so if you're on the Earth, if you're walking around, you have a notion of what a straight line is, right? You can walk in a straight line on the Earth in any direction, right? But if you zoom out and you look at the Earth, right, then you're not really walking on a straight line, right? You're walking on a great circle on the Earth, right? If you kept walking in a straight line, you'd eventually come back to where you started, right? You could walk around the equator, or you could walk in some other direction. But your straight lines, if you think you're walking in a straight line on the Earth, you're really walking on a tiny little part of what's going to end up being a circle around the Earth, right? So you're not really walking in a straight line. So the lines, when we're talking about this elliptic geometry, which is basically geometry on a sphere or on what's called an ellipsoid, so it can be a little elongated, is that the lines are actually great circles, which means circles on the face of the Earth that break it up into two equal halves. So like, for instance, the equator. Okay. And what we have is these two lines, any two such lines meet. So for instance, we know that the equator intersects every meridian, right? These are two ways of, and if I draw any two of these big circles on the Earth, they're always going to meet. So if I have the equator and I have some other point and I'm going to walk in one of these great circles around the Earth, it turns out that it's always going to meet the equator. So in that sense, there is no parallel line through that point. And furthermore, we have some weird stuff here, which is that triangles in elliptic geometry have angles that sum to more than 180 degrees. Okay? So let me draw some pictures to show how this makes sense. So let's say we're on the Earth. So I'm going to draw the Earth. So this is the Earth, and this is my equator. Okay, so that's the equator. So in the equator is a great circle, right? I mean, so if you walk straight in, and now let's say, so this is going to be my line, which I'm going to call L. So now let me take another point on the surface of the Earth. Let me call it P. And so what's a line through P? Well, a line through P means you start walking in some direction and you just keep walking in that direction no matter what. And anytime you do that, what you're going to do is you're going to trace out another equator of the Earth, like not the equator, but another circle around the Earth that cuts the Earth up into two equal halves. That's what happens if you start at one point on the Earth and walk in the same direction until you get back to where you started. Okay? So for instance, any line that you could draw through this point of the Earth, it might look something like this. Okay, or it might be a line, I'll draw another thing. It might be like a line of longitude, right? You could have a line of longitude over the Earth, goes from the North Pole to the South Pole, and then goes back here, comes on, and so be it. And what we see is any two great circles meet. Okay, so given a great circle, which is what a line is on the Earth, so given a great circle and a point not on the circle, and maybe I'll give the point a name, I'll call it P, then all great circles through P meet the original great circle. Okay? And so this is a violation of the parallel postulate. So what we're saying really is on Earth, the parallel postulate doesn't work. If I have the equator and I start at any point of the Earth not on the equator and I walk in a great circle, I'm always going to pass the equator at some point. I can't find two parallel great circles. If I try to just walk like what looks like parallel to the equator, like walking in a circle like this, that's actually not a great circle because it doesn't cut the Earth into two equal parts. And if you actually tried to walk just along a line of latitude, along a parallel, then you would actually be changing direction. It wouldn't feel like walking in a straight line the entire time. You'd have to like curve slightly to your left to stay on the parallel. Okay, so if you're actually going to walk in a straight line, you're going to meet the equator at some point. Okay, so the Earth is basically a model of what's called elliptic geometry, where the Playfair postulate fails. Because if I have a great circle and I have a point, then there isn't some other great circle that's parallel to the first one. In fact, they all meet. There's nothing parallel. Okay, so this is what's going on in elliptic geometry. And all of these great circles always meet. In fact, they always meet at 2 points. And so you really don't have any parallel lines. Okay, any questions about this? And it's a bit of a weird concept if you haven't thought about it. All right, well, let me show you another picture which is what a triangle looks like in elliptic geometry. Remember, I said that a triangle can have angles that add up to more than 180 degrees. Well, what happens with this triangle? So here's a triangle on the Earth. One vertex is at the North Pole over here. One vertex is over here somewhere in Indonesia, it looks like. And then another vertex is over here in the Indian Ocean, right? And what you can do is draw these at an angle of 50 degrees. If you make a 50-degree angle at the North Pole, and then you have each of these go down to the equator, well, when you're at the equator, if you're going on a line of longitude, and then you just start walking along the equator, that's a right angle, right? You walk down to the equator along a line of longitude, and then you start walking along the equator. Those things are perpendicular to each other. It's a latitude line and a longitude line at the equator, right? So what you have is a triangle here on the surface of the Earth where one angle is 50 degrees, another angle is 90 degrees, and another angle is also 90 degrees. So the angles here add up to 230 degrees. And in Euclidean geometry, you can't have that. But in elliptic geometry, you can. So on the surface of the Earth, if you draw a triangle, what actually happens is that the angles always add up to more than 180 degrees. Now, you only really see this if you draw a very, very big triangle, right? This triangle is taking up a lot of the Earth. If you draw a small triangle in a small part of land, so just like within some city or something like that, then the Earth is almost flat within a city, and so the angles of the triangle will basically add up to 180 degrees, although they actually will always add up to ever so slightly more than 180 degrees, because there is some tiny amount of curvature going on, even in a small part of the Earth. But it might add up to like 180.0001 degrees, instead of which you're not going to be able to notice. Whereas if you draw a big triangle like this, it really adds up to 230 degrees. It's something big. Okay, so on the surface of the Earth, triangles add up to more than 180 degrees, and you violate this parallel postulate. So it's just a different geometry, but understanding this geometry is very important if you're whenever you're working with the Earth on a large scale. So if you're doing navigation or you're doing astronomy or anything like that, then you really have to work with this elliptic geometry. You know, plain Euclidean geometry isn't going to be good enough to understand what's going on the Earth. All right, any questions about this?
Yeah, Andrew?
Yeah, Clinton?
Yeah, so the angle between the lines of latitude and that of the lines of longitude is exactly 90 degrees?
It is exactly 90 degrees as long as you're at the equator. It's exactly 90 degrees at the equator. It can be less than 90 degrees if you're it can be less than 90 degrees if you are wait, no, let me rephrase. No, yes, it's exactly 90 degrees. Yeah, the lines of latitude and lines of longitude are exactly 90 degrees. Yeah.
Oh, okay.
Yeah.
So if we draw another triangle on the Earth, and as large as this triangle, the bottom angle will always be 90.
Right, but depending on, so the size of the triangle is actually going to basically determine how much the angles add up to. You can figure it out based on the area of the triangle. There's a formula that relates the area of the triangle to the sum of the angles.
Oh, okay. So in Euclid, in elliptic geometry, there is no sort of maximum value to which the angle of a triangle can add up to.
There is
no maximum value.
No,
right?
there is a maximum. I mean, for instance, all the angles themselves all have to be less than 180 degrees. So for instance, they can't add up to more than 540 degrees because each angle has to be less than 180. I think probably you can't get bigger than 360, although I have to think about that a little more. I think, let me actually see. So maximum angle sum of spherical triangle. Let me just see. Yeah, so the number, the maximum, the sum of the degrees has to be less than 540 degrees. And that's because each angle has to be at less than 180 degrees.
Oh, okay. It's less than, not less than or equal
not
to.
Less than or equal to. Has to be less than,
than,
because each one has to be less than 180 degrees. Yeah.
Okay. Oh.
Yeah. Yeah, so that's a good question. Okay, so this is elliptic geometry. Let me show you what hyperbolic geometry looks like. So with hyperbolic geometry, so elliptic geometry, we think of it as like geometry on a ball, basically. Hyperbolic geometry we think of as geometry on a what's called a saddle-like surface. It's a surface which has what's called negative curvature. And lines are a little bit harder to describe, but we can still think of the line between 2 points as the shortest path from one point to the other point. And what we see in hyperbolic geometry is that you can have many lines through one point that are parallel to a given line. And the triangles in hyperbolic geometry have angles that sum up to less than 180 degrees. So let me show this in a picture. So this is kind of a picture of a saddle surface. So if you want to draw a surface like this, you can take this as like x squared minus y squared equals z squared. Or you can take it like, you know, z equals xy, I think should work. So that there's various different equations that you can use for surfaces in the XYZ plane that give you things that look like this. And so, wait, let me rephrase this. I don't think we want x squared minus y squared equals z squared. Sorry, I want x squared minus y squared equals z. So what we have here is, let's look at this line over here. I'll draw over it in red. So here's a line. And of course, the lines looked curved because you're on a curved surface. But this is basically, if you're just trying to go in the shortest distance between 2 points to get from here to here, the shortest way to walk is going to be like this. And now what we see is we have these two other lines here. So this one and this one. And the green lines that I drew are both parallel to the red line, right? Neither one of these is going to meet the red line. So we have two lines through this point that go in different directions, and they're both parallel to the same line. Whereas remember, in Euclidean geometry, if I have my line and a point, then there's only one line that's parallel to it. So here we have two lines, and in fact, there are more. There's going to be infinitely many lines through this point that are parallel to this line. Okay, so this hyperbolic geometry is also different. We have lots of lines through a given point that are parallel to the same line. Okay, and on top of that, if we look at the triangles, the angles in a triangle will add up to less than 180 degrees. And here's a picture, right? So we're on this saddle-like surface in what's called hyperbolic geometry. And if I draw a triangle, these lines, these are basically the quickest way to get from this point to this point. So these sides are all lines. And what we see is that these angles in the triangle add up to less than 180 degrees, right? In fact, they add up to, in this case, it looks like a lot less. It looks like these angles might only be about 20, 25 degrees each, right? So maybe these angles add up to 75 degrees or something like that. Okay, so I'll just say, so angles add up to less than 180 degrees. Okay, so we have these other two geometries. So hyperbolic geometry it's maybe a little less clear where it actually gets used, but it turns out that hyperbolic geometry is very important for understanding the theory of general relativity. So if you want to understand like Einstein's space-time and, you know, how gravity works in the large scale of the universe, then there's a lot of hyperbolic geometry going on there. You know, it's important for understanding black holes and things like this. Whereas Elliptic geometry or spherical geometry is much more down to earth, right? That you really see even just on the surface of the earth. You don't have to be thinking about Einstein or anything like that. That's already useful when you're just trying to navigate in the water, right? But both of them are these examples of non-Euclidean geometries. And so it shows that even something obvious like the parallel postulate is actually not that obvious. And if you try to imagine a world where it doesn't hold, then you get these other, interesting mathematical concepts that actually turn out to be useful and to describe real things like general relativity or, life on the surface of the earth. Okay, so this is just a very quick introduction to non-Euclidean geometry. I'm not an expert in non-Euclidean geometry. I don't know a ton about spherical trigonometry or anything like that. There are certainly people who know a lot more than I do, but this is kind of a basic introduction here. And so I just want to say so as always, thank you for your attention. There's not going to be class next week because I have meetings that day. So on February 9th, no class, and we'll resume February 16th. There's no standard homework this week, although as an assignment, if you're interested, you can read the Wikipedia article on non-Euclidean geometry and where you'll see some of this stuff. But I am going to send out a survey either later today or maybe on Monday. So a survey talking about what topics you're interested in covering in the spring. Okay, so you can ask for anything you want, but there's some choices. So we could do proof-based Euclidean geometry. We could talk about trigonometry, although we did that a couple years ago, so some people may have already seen that. We could talk about conic sections. We could talk about conic sections. We could talk about logic, and anything else that you want to do. Okay, so anything in the curriculum that you want to do. The only thing is I will try to do something that is in the curriculum because people have said that is what's the most useful for what we should do. So I'll send out a survey and you can fill it out, and I'll decide what we'll do for the rest of the semester based on that survey. Okay. Good. All right. And anybody, again, if you didn't write in your name, please do so. But it looks like most people wrote their name. All right. And so any questions about non-Euclidean geometry or anything else, I'm happy to take them.
Yeah.
Yes, Clinton.
Andrew?
Yeah.
Yeah. When you were explaining the concept behind hyperbolic geometry, I kind of see the graph of the hyperbola right in the graph there. But then if we do the graph for hyperbola on a piece of paper, we realize that those two lines that go opposite each other, those two curves that go opposite each other,
These ones, the green lines?
Not actually a line, but it's a curve.
Yeah.
So I was a little bit, the red.
The red, yeah. Okay. Right. So the problem is you can't, if you're on this surface, if I want to walk from this point to this point, I can't just walk in a straight line because I'm going to leave the surface if I do that, right? The straight line from this point to this point doesn't lie on this curved surface. So we need to expand our notion of what a line means. And for us, what a line means is it should mean the shortest way to go from one point to another point on the surface, right? So this is sometimes this is called a geodesic. And so if I want to walk on the surface from this point to this point, then the quickest way I can do it is by following this red line. This turns out that this is the fastest way to stay on the surface and go from one point to another point. So in hyperbolic geometry, this is what we call a line. A line is still the shortest way to get between 2 points. Okay? Just like on the surface of the Earth, if I'm on the equator and I want to get somewhere else on the equator, the shortest way to walk there is to walk along the equator. And if I walk along the equator, that's not exactly a straight line, but it feels like a straight line while I'm walking there, right? And so that's exactly the same thing. If we lived on a saddle, then what would feel like a straight line would be going the shortest way from one point to another point. It would feel like you're going straight and you're not turning. And so in math, this is called a geodesic. But it's your substitute for a straight line.
Thank you.
Okay, you're welcome. Other questions?
Thank you.
All right, you're welcome. Thank you, Sange. I'm gonna say anything else or anything administrative going on? It seems like everybody got their data, so that's great.
Yeah, I will send the report tomorrow.
Okay, great. Thank you. All right, I'm gonna stop the recording.